Hey, how you doing? Welcome back to the channel. So here we go. We're back to our VFD vacuum fluorescent display project here. And so what I'll do here is see we got one digit up and counting. So what I want to do is I'll just really quickly go over what we have for the design really quick. We're going to share the screen. So I think that should be okay. I said to share the other screen and it blocks it. That's just wonderful. Okay, so as we were discussing before, a few things. So we have this VFD clock that we're making, and what I'm going to do, blah, blah, blah. Why? Okay, yeah, and so here's the idea for this clock. So we're gonna have this clock, and it's gonna just like the hours, minutes, seconds are gonna be kind of your typical standard kind of clock. But we're gonna have this other long-term countdown ability in there where we can count down years, months, and days. And then we're also gonna have some other displays here potentially. So that's kind of what we're working on now. I'm trying to work on a single digit right now to kind of get the basics down of it. And so what I did, so yeah, so here's like a single digit setup. Now, the idea here is going to be, okay, yeah, so what's happening here is we have, we're gonna have a PC plugged into a USB cable plugged for this PIC microcontroller. This PIC microcontroller is this Curiosity HPC board. And as I noted that the power on this board is coming from the USB, and I really want to make sure I isolate it. So I put these opto isolators in here. So we'll go over that really quick. But basically, we're going to isolate the two power domains. And what we're going to do is we're going to bit bang, meaning we're going to like literally serial data, serial clock, and then we'll have this read clock, this R clock that will like shift things in. So what's going to happen is we're going to have the shift register, and we're going to shift in the word that we want to write into the shift register. Then we clock the R clock, which will clock it to the outputs, and then it'll go to this driver chip, this UDN2981A, which provides extra current to drive the VFD, and then that will drive the the display, the particular things that we want. Okay, so now let's go over a few things here. A VFD power. Okay, so I went through this. We have a wall port over here with 30-volt supply, 5-volt logic, and 1.5 for the cathode. One of the things to note over here is that this 1.5 is running kind of hot. That chip is really hot right now. But the other thing that we did is I've lowered the voltage to 20 volts. I basically didn't find any benefit to having a higher voltage on there, so I played with it, and it seemed just as bright without. I think that because in this case, if I go back here, what's going on is I'm just going to leave the grid on. So I'm not actually time division multiplexing. I think I might need a higher voltage if I was going to time division multiplex, meaning that I would take the grid for each digit and I would strobe them one at a time. I'd say I'd strobe digit 1, then digit 2, digit 3. So then all lighting at the same time, but you do it really fast, so it appears that they're all lit at the same time. Like for example, if you do it at 60 Hertz, then you're not going to, you wouldn't notice necessarily. But I'm not doing that. I'm enabling all the time. So I think the lower voltage is fine. So here's kind of the test setup. So this is really the basic logic that we have. And so here we are drawing this out. Now what I'm going to do is pin RA 1, 2, 3, and 4 from the PIC. I'm going to define these guys and I'm going to run them through the optocoupler. And I've just labeled them here. We have this serial clock, which is S clock, S data, serial data, R clock, which is the register clock. So that's what we use to apply the shifted value to the driver. And then grid just is for enabling the grid on the tube. So what happens is the opto actually inverts it, it turns out. So it's going to invert it. And so I'll handle that in the firmware and the PIC side. But what happens is basically it goes into the shift register, it shifts it in, and right now I'm just leaving the output enable on the shift register tied off to 0 actually, so that's incorrect. This should be, do that. Take this guy here and we're going to put it to ground. And this will be ground. Now what, I want to note that if I look at the opto circuit, where's the Opto? Yeah, so here's an example of the Opto circuit. I actually had some trouble with this thing. The first problem I had is I didn't realize I bought a PIC part that has an F in the name, and that's like a 5-volt part. But here's the thing: it's not a 5. It's not going to drive the logic at 5 volts. It's just 5-volt tolerant. So it's still, the logic is being driven out at 3 volts. So my original equations that I was using, the values that I was calculating incorrectly for the resistor. So originally I came up with, I showed here, a 1K resistor here, and that's like too low. So it really needed to be a 5K, because this PIC power pin, the power on the PIC is really only driving to 3 volts. So really quickly, here's the equation. So basically what we have is we take the 3.3 volts being applied by the PIC minus the 1.2 volt drop over this, the diode, the LED diode that's inside the optocoupler, okay? And that tells you what we want R1 to be. So R1 is this voltage divided by the current. Now the 4 milliamps is the target for the current threshold that we've set. Okay, and so we get a 525 resistor. So we basically work out to 560. Now the other side stays the same, and we work out that we need a 1.2K resistor on the other side. Now, this picture is not accurate. No, I'm sorry, it is. Note that the grounds, we have the PIC ground over here, is a different ground than the, geez, I cannot believe this. It's so funny. It's like so bloody annoying. This is the VFD. It's like I had this right. I swear I had this right. Okay. So for each of these 4 lines, you're going to have the PIC is going to drive out the signal here. And it drives through this resistor into here. And then this value is 560 ohms we settled on. Okay. And it's going to go through the opt isolator. So we have over here the PIC power and the PIC ground. And it's totally separated, isolated from the VFD power supply and with 5-volt supply and the VFD ground. And we can show that, we'll just show that, basically we did these calculations, and we'll show that isolation on the actual breadboards. But let me show you this. So these clock, serial data, R clock, everything goes into this chip. It basically gets shifted in. We're leaving the output enable all the time. And every time when you R clock, assert the R clock, it basically clocks the shifted value in, out. The values then come out to this UDN2981, which just provides the current drive. And then this directly connects to the IV11 tube. Okay, so this particular tube, let's see, so I'm going to stop share and I'm going to share another one here. I hope this is all coming out. Share this one. Okay, I think it is. All right, and I want to go digital mapping. So, so here what I had to do is I had to come up with a mapping for this. Now, here's what I noted. I literally, for this IV11 tube, I literally don't have the mapping of like which pin specifically lights which segment. So I had to experiment with it. So I did, by experiment, I determined that, these are pins 3, 4, 5, 6, etc., which segment they light. Okay. So basically on the picture, you can see like the top horizontal bar is segment A, then the middle one is G, bottom one's D, etc., and DP is the decimal point. So you can see how basically map that out. Now, here's the shift register. So we're shifting, so the shift is going to be left. So it's a left shift. So what happens is the first bit to go out is going to be the one that's going to end up in QH. So we're left shifting. So you start, so basically, this is going to be the value that you want to shift out. So in the firmware, to have a digit of 0, I want to send out a 8-digit, a byte called ED. I want to send that byte out, and I'm going to shift it starting with this bit 1, right? So here's the binary representation indicating where it's going to be, and then which segment it's going to light, and then the detail of what pin it's actually going to. And this is going to be the value we send in the firmware. So what we're going to have is just a little mapping table in the firmware that's going to map, if you want to send to 4, it's just going to shift out 3, 5 hex, and then that will light the appropriate digits. Now I want to, and left shifting, yeah, so it's going to be a left shift. And so I just want to point out that, you can kind of create whatever mapping you want. And if we look at this, this is kind of just a simple wiring. So let me just show you what I mean. If I go back over here and I share my picture here, basically QA that we were talking about is going to basically pin 10 up here. And then QB ends up being wired here. See how I wired those up, and then the next one, et cetera, in order. And so that just ends up being the mapping, right? And so what I wanted to point out, that these pins can be wired any way you want. See, because like if you look here, if you physically look at this pin 1 on 7459 goes out and it goes and crosses 5 other lines here. Now this is virtual crossing. Like we're not, like if we were doing a real printed circuit board, yeah, we want to avoid that. And there may be another way to do it, like we could go below, but you can see that we have a lot of crossing here, okay? So you don't have to do it this way. Like we literally could wire these 2 chips up any way we wanted, right? Think about it. You can permute this wiring any way you want, and it doesn't matter. And because you can just map it in the firmware. So if you go back and you look at the mapping table, if I, for example, said, well, gee, I need to shift and I need to attach pin QB to G instead, you could just make that change, and then you would just update the mapping table. And all your firmware, right, most of your firmware is going to run on the digits. We're going to have our calendar, our clock logic, all running on digits, and it's just like, okay, update the digit, send out the new digit. It just calls a function that's going to map it to whatever your mapping is. So I just wanted to point that out because this is what like they do in real world. PCI Express especially has this. They have like for all the lanes, so you could have a 16 lane, 32 lane, 32 lane, I don't know if they go that high, but 16 lane serial interface. And so each lane, literally the PN can be swapped, right? So you can have basically the line, the bits would be inverted. You have PM swaps, you can have ordering. So which lane, physical lane holds bit 0 versus which holds bit 4, 3, or 2. These can be ordered either way. And then there's a bunch of other things that can be done in there. And so my point is that obviously this is really simple stuff, but this is a very common thing to do because you know, we do this really simple stuff in here. And then when it comes to laying out the board, you have this ability to reduce the layout stress on that, right? So basically, you know, it just reduces the layout stress. So basically what would I do here? If I wanted to make it really like fancy, maybe I'd leave the pin QA up here going around to here, but then QH would go directly to 2, QC would go to here. So I can make them all go around without overcrossing each other, and they would just come out to the left, over and back. And we could do that mapping, and it would be like a much more efficient board layout. So really simple and silly, that's kind of what we have. So that's what we have. And then, so let's do this. And now I'm going to show the code really quick that I have. So now what's going on is the tool. Where's the tool? Yes. Okay. So here we are. This is the pick software. So what I want to do is I want to go through you know, the main section of code here. So just keeping in mind that everything gets inverted by the optocouplers, okay? So basically what I start out is I initialize everything. And so what I'm doing is I'm basically setting all these low. So I'm setting S clock low, S data low, R clock low, and grid low, and then I'm making grid high, okay? So I'm actually just enabling the tube, the grid on the tube. And then I come into this while loop. Now this is all within the main. So this is gonna come in here in your C code, right? You always enter it with main, and has a system initialized. Now this function is generated by the tool for you. You have the tool where you can simply define what the pin's gonna be, and it'll put all that helper code in there, and that all gets done in there. But then this runs forever. Wall 1, so it's just going to run forever until we kill the program or turn it off. And so what am I doing? I'm counting. I have a for loop. I'm counting. I declare integer 0 to 9. It's going to count, right? So I will go 0, 1, to 9. It'll be at 9. When it goes to 10, it's no longer less than 10, and it will exit the loop, come out of the loop. Since it's infinitely, it'll go the next iteration of the wall and just repeat and just keep repeating. Now, what is it doing? Send count, send digit. So this is the digit I'm sending. So here I'm counting from 0 to 9, and I'm sending digit 0 to 9 through the display. And then I have this counter function, which is going to be a delay. So let's look at the counter function first. Counter function, really simple. I just come up here and I just have a count. All right. So basically, if you have a count to 2, it's going to count. This counter will count from 0 to 1. Right? And it'll just count. So I can have different delay. That's what this is doing. It's just creating a little bit of delay. Probably better ways to do it, and we'll work on that in the future. But for right now, just do a little simple counter to add delay. Now, so now let's look at the send digit function. So this is sending digits, human readable digits, 1, 2, 3, etc. That's what we're doing. So the send digit function is right here. So send digit, what we're going to do is we're going to map the digit, right? So we come into this function and we're going to call get digit function, and we're going to pass the digit that we want to send, and we're going to return, we're going to get the map it. So let's look at our map function. So this one, once again, we have a digit. Now the unsigned integer 8. I have some integers floating around. I should and I will fix those to be used like unsigned integer 8 or int 8. These are just defined to be 8 bits, because normal integer in C would be 32 bits signed, I believe. I forget, but so normally, like especially firmware type stuff, you want to control what your bit widths are, and they have these defined, so it makes it really handy, defined and treated as 8-bit. This is incorrect mapping here. So remember the mapping table that I showed before? So this is just implementing the mapping table, and it's implementing it in the simplest possible way of just like, look, the digit 0, just like we talked about, we're going to send ED. 05 for 1, etc. And then I just have the default statement where I just send all the digits. So it will return this value. So this function does the mapping. So we're going to minimize it. Okay, so once we've got the map digit, now what we need to do is we need to send each one of those bits. And this is where we get into what we call bit banging. Okay, so we're going to send each bit out. We have to write an instruction to literally put the data bit out, and then write another instruction to set the clock high, then we set the clock low, and then we go on to the next bit, etc. That type of a thing. Okay, and then how we do this for the send bit, what we're going to do is we have 8 bits. We know all, or we're sending 8 bits in this case. And what we're going to do is we're going to do an and. So what we do is what this and operation will do, what's happening is you take I, and you're basically moving the 1 in the position. So when I is 0, you have this value is hex 01. And then when it's 1, it comes 2, then it's 4, then it's 8, etc. So it's moving up. So there's only 1 bit set. So what it's doing is it's isolating that 1 bit. Okay, so that's what this thing is doing here. This function here is isolating, has a single bit set. All the other bits are 0. Now, when you and a 0 with any other bit, you get 0 out, right? And so this is the bit and function, bit and operator in C. So what that means is this is going in, and it will start with giving you bit 0. I'm labeling bits from 0 to 7. So 8 bits, it labeled 0 to 7. So we start with sending bit 0. We call it with that, and then we call it with bit 1, bit 2, and bit 3. Okay, then we go to send bit. Now the send bit function each time, this is where we have to actually send the bit. Now the SData line, this function was set up for us by the helper tool. Basically it says, okay, it gave us this function. It said, I labeled this pin, an IO pin as SData, and it has the actual physical address of that pin, so we can set it high or set it low. Now what I do over here, notice that I don't shift it back over here. So what's happening is when I'm up at like bit 4 and I and 4 and there's a 1 there, okay, what am I going to get out? It'll be a 1. Now if that bit 4 in bit position 4 was 0, then the output is still 0, right? So it's either greater than 0 or it's 0. And anytime it's greater than 0, I'm going to set low. I'm setting the bit high, right? So remember, we're inverting here. We're inverting for the optocoupler. So it's just a way of like, I'm not shifting the bit back because I don't need to. I don't need to waste the code of shifting it back to the bit 0 position. I can leave it up there and just look for anything greater than 0. And so very careful, we're inverting. So if the bit is a 1, we send a 1 out. Bit is low, we send a 0 out. Then what we got to do, but now we've set the bit, and now we have to wait a little bit, and then we have to actually toggle the clock. So we have to set the clock to 1 and then set it to 0. And then after that, we basically are going to exit, and then we go to the next bit. Now, interesting, I didn't set any delay after that bit. Interesting. And it's working reliably at this point. So, okay, so this is how we're sending it. So that is the what we're doing. So I think let's go ahead and look at this on the oscilloscope, and you can see how this is operating. So let's do this. Okay, so we can see that what we have here is there's your PIC controller here. So you have your PIC controller, and I want you to notice how these are really isolated, right? These optocouplers are right in here. These are the optocouplers. Up here is the VFD supply, 5-volt supply. This one is the PIC supply. They're totally isolated. The grounds are not connected together between those two rails, right? Those grounds are not connected. They're totally separate. If I connect those grounds, I'm going to lose it, right? I'm going to lose the isolation. If I connect the VCC, I'm going to lose it. Okay, so those are really isolating. Now, what I do is I have 3 volts here. This is PIC is operating 3 volts. I send these guys over to the input side of the optocouplers. The output side then go over here to the top chip. Here is going to be your shift register. And so that's where it's going to shift it in. And notice I have the coupling cap on there, decoupling cap. And then it goes to the second chip down there under the Pixie is going to be the driver chip. And see what I did is I just stuffed the pins of the Dixie tube right into the same controls of the pins. So it kind of just less wiring that way. And you can see here, our thing is counting. Now, right now, it seems to be counting pretty reliable right now. Really that bypass cap really helped by eliminating some of the noise. Okay, so I just realized something. I was looking this up. You know, I'm getting these digits are skipping, and I was pointing out how I thought it was the bypass capacitor. You know, there was noise in there. I mean, that could be related to part of it, but I don't think that's what it is. I think if we go down to the scope, I can show what is actually going on. If we remember, these opto isolators turn out to be really slow. And so now this is the logic of the clock zoomed in going to this is the clock input to the shift register. So basically it turns out this is way too slow. If we look at this guy, we are at 2 microseconds per division. So each square. So if I look at this is my second cursor, right? Right here I'm moving. So looking at the starting point, we have about 3 grids. So that's 3 grids times 2 microseconds per, that's a 6 microsecond transition time. Now that is really, really slow. And so what's happening, you can imagine that as that signal is transitioning, it's spending a lot of time nearing that switch point. And what happens is any noise on there or anything like that at the point where it's actually going to switch the output, you know, it could cause it to trigger and do multiple things. You know, basically it could like trigger and cause multiple clocks, and that's what's happening. So that's why I think when you look at this and you see that you'll get this, you'll get kind of every now and then, and it's not very often, it's actually pretty good, but every now and then you'll get a weird digit. And what's happening is when you get that weird digit that you didn't expect, it's happening because the shift, you got a double clock or maybe a triple clock or you missed a clock. And so in the shift register, so then basically the value that we have wasn't correct. And then it's being applied out. Our clock is okay, it's being applied out. So what's happening is basically my optocouplers are so slow that it's a problem. So now let's do this. Okay, so we can see here looking at the SM74HC595 data sheet. So we can look at this data sheet, and we have a 74 series, not a 54, 595. So this is our shift register, and we can go down here and look at absolute max ratings, ESD, other stuff. But what we're going to look at here relative to this is the recommended operating conditions. And we're going to zoom in here, and we see that they have something here called delta T, delta V, input transition rise or fall time. So this is where the area where I think we're having trouble. So as I pointed out, we have about we we have like 6 microseconds of transition time. Now, the transition, I mean, there's the real part of it is it's not the whole range, but still, even if it was only 1/3 of that at 2 microseconds, here for our 5 volts, you know, we're 5 volts, so we use the 4.5, you know, they're recommending a maximum of 500 nanosecond transition time, okay? And we're at somewhere between, estimate 2 microseconds to 6 microseconds. So we are whatever you call it, 12 times that. Okay. So we're way too slow. So that I think is what's going to explain what's going on here. Yeah, because here they're talking about if device, so it's note 2 here, if device is used in the threshold region, 0.5 to 1.5, there's potential to go to the wrong state from induced grounding, causing double clocking. Double clocking. So double clocking on the shift register, what would that do? Double clocking on the shift register, you know, give me an extra shift through, and then I get the wrong value in there. So that's now what I believe to be the case. So what we're going to do then is we're going to go look at these. So what I need is another chip. Now, I can try to play with the resistors, and maybe I will play with the resistors on the Opto isolator. And another option might be to actually add a transistor to the Opto isolator to make that output circuit work faster. But one of the solutions is to just put what's called a 74 HC14. Now, what this is an inverter. Now, this is going to work out nice, because this is an inverter, but it's a special inverter. It's called a Schmidt trigger inverter. And so what this does, it's got high noise immunity, but what it really does, so it looks like this. So logically, all it's going to be is an inverter. So now the output of my optocouplers that are inverting, I'm going to invert them again. But what I'm really getting, so that's going to clean up my code in terms of I don't have to invert the code. But what that is going to do for us is this thing is tolerant of basically any rise or fall time. So it can be really slow like we have, right? Because it's made for, there's other things that you could interface to that could have very slow rise fall, and you want to get a clean logic output. But let's see here, where is the output? HC types, propagation delay, and we want this guy. So we look through our specs. So that's one of the things, like when you're doing these things, you got to look at all these data sheets. And, you know, honestly, you know, I haven't looked at many of them for years, but you just kind of, you know, you kind of figure it out. So this is the one that I'm interested in here, output transition time. So it's T, capital T, LH, and then T, HL. So that's low to high and high to low. And here the test conditions, so this is a 50 puff load, and we're really interested, right, in the 4.5 volts. And you can see here that for our part, now we're not doing this extended range. I think we're going to be in this range here, but basically it's going to be 19 nanoseconds now. So we're going to go from a 6 microsecond transition time to a 19 nanosecond transition time by adding this. Now we're going to add propagation delay, which would be like 34 nanoseconds. So it's significant propagation delay, but we're going to get nice clean edges out. So that's what we're doing. So that's good. And then the thing over here, this right chip over here, this guy is this guy's just for the grid. I need a driver for the grid as well. And so a bunch of extra inputs there. And then over here, these are my power supplies. So we have this one over here is the 5 volt in front. So notice I have no resistors. I replaced it with a 7805, so I don't need any resistors. They just internally trim it so that you get 5 volts out. Then I have the higher voltage 20 volt, which I'm at, and then behind there in the back is the 1.5. Now I have my probes, and I'm probing right now S clock and S data. And so we're going to look at that on the scope right now. And so if we look at that, and sorry for all that. Okay, so here we are, our old school scope, and we're at 2 volt per division, and now 1 is going to be the clock, okay, and 2 is the data. So you can see as the digits are going through, you can see, you know, what's going on. You can see how I have this set up. So let's see if I can zoom in a little. Let's see. Yeah, so you can, so this is what's going on. So you can see the data is in the bottom. You can see how the data is changing for the different digits. And you can see how I've really just centered the pulse. I'm being really, really just slow and conservative about this in terms of how I do that. And what I did, see the pulse, I think when you looked at the code is I held it for like 2 counts or whatever, because what was happening is the optocouplers are kind of slow. And what I would see is this kind of runt pulse coming through, and it would create problems. Like if I don't give it enough time, if I try to like set it high and set it back low too quickly, it will just, freak out. Now, let me look at the R clock and show you the R clock here. Now I'm going to go here. Hopefully I don't cause a problem. And we try to catch the R clock. Okay, so that's all good. Gosh, it's still counting good. Okay, so now I have the R clock on the second one. So let's see. Okay, so there's the R clock. Okay, so over here you have your shift clock. You're shifting in your data, and then below it you have the R clock at the end that actually applies it to the output. And let me see. I'm going to zoom in here. Delay. Okay. And I'm going to do this guy. Okay, so we can see that a little better. Yeah, and so you can see here actually that, well, it is getting to 5 volts. That's good. But I could almost even hold the R clock a little more. So this is what I wanted to show you, what it might look like if you don't have enough pulse on R clock. So let's go look at that really quick. I'm going to share that. This one, share that. Okay, so put that over there. Okay, so we're looking at this guy right now. So where is the R clock? After we send all the digits, blah, blah, blah. So send digit, yeah. So here's where the R clock. So what I'll do is I'm going to cut the R clock width in half, and we're going to see what happens to that. And what I did do, I'm going to build it, program it. I wonder what that message was. There was a message in there. Okay. Okay, wait, I saw a problem. What was the message? It was telling me something. Int to uint, unsigned. Okay, that's just a warning. That should be okay. So that's fine. Okay. So build successful. Okay, so I think it's okay. So C compiler is just complaining about your ints and stuff, because you shouldn't be passing ints to uints, etc. It just is a mess. Okay, so let's see. So it should be running again. And now let's see what's happening here. If I look at this, it seems to be broken. Let's see what's going on. It's really messed up. So let's see if we can figure out what's going on here. Okay, so this is exactly what I want to show you. The bottom one is the R clock, and look at that. Now this is 2 volts per division. So this R clock is barely getting over 2 volts. And because it's getting barely getting over 2 volts, what's happening is it's not always clocking. It's basically not always properly clocking in the shifted value. So that's why one of the problems that we just need to be cognizant of, and I see, yeah, you can see that it's not clocking in the right value. So here the shift register is shifting in okay. It's shifting in every time, but the R clock is not able to do that. Now, if I reset, I'll get a different value. Reset, I'll get a different value. But this is because that R clock is basically too small because it's not long enough. The pulse is not wide enough. And we have this long delay in getting, the rise time through the optocoupler. So now go back and we go back to this one. And where did I do that? Yeah, this guy right here. And you know, let me do this. Let me just set the count to 1 here. I think I have a problem in the function where I set it to 1 or something. It's not really working the way I want it to work, but we'll just try it. Let's see what happens here. See, warning integer to int 8. So that's not really a big deal. That should be fine in terms of functional, but it, yeah. So now here we go. And we have our counter counting again. So that is good and it's stable. Okay, yeah, so something really weird's going on. So once again, let's not get too distracted on that. So if I just call it twice, I'll debug that. And let's update it. It could be that message. It could be that message telling me something. But let's go back to our stopping share. We're back to working. We're working, okay. Back here, okay. Yeah, so here, and you can see then we've got the pulse. You can see that the pulse is working. So, so that's pretty good. It's interesting. So if you look at these pulses, it's like for whatever reason, the charging up, the rise coming through the optocoupler seems to be slower than the fall. But so that's it. So this is now working. So we have 1digit working. I think I'm happy with the power supplies and everything. So now really the next thing is to, you know, I'll fix my delay function and then kind of actually put some clock functionality together. So I'm not sure all the details on what I'm going to do next, but I definitely have to put like at least pairs of digits together. And yeah, there's a lot to do now. So, but at least the basics of the Nixie are running and stuff like that. And so I think that's it for this one. Talk to you later. Bye.